All right, so welcome to multi-variable calculus. Let me just quickly review where we've been in the last few times. So we've talked about equations of lines. And so the equation of a line, x, y, z is some initial point plus t times some slope vector v. And we can write it parametrically, x of t, y of t, z of t. And so this is the nice generalization of what we did in one dimension. It extends very naturally to higher dimensions. We talked about how derivatives of standard functions. We talked about how a partial derivative is really the same as a regular derivative. When you have more than one variable, this just means hold every variable fixed but the one you denote. And so this is a generalization of the df/dx notation from before. We're now using a curly d to denote that it's a partial derivative. We sometimes write f sub x to mean the derivative with respect to the variable x. So if I give you the function f of x, y, z, say x squared y plus 3y cubed cosine z, when I take the partial derivative with respect to f, df/dx, that means consider y and z constants.
Didn't we do this last year?
I'm just, no.
A little.
Oh, we did a little bit because you had a calculus professor who would teach you a little bit of multivariable calculus. So just quickly, because it's been a while. So in calculus, the big idea is that locally, a differentiable function looks like a straight line. And so we talk about tangent line approximation. You're given a f of some point on the curve. The slope is f prime of a. We write down the tangent line. And there's a couple of ways of writing the definition of the derivative. The standard is the derivative at a, f prime of a is the limit as h goes to 0, f of a plus h minus f of a over h. That's the same as the limit as x goes to a of f of x minus f of a, just let x equal x plus a. But another way of writing it is it's the limit as h goes to 0 of f of x minus f of a minus f prime of a times h over h. And what this is saying is take some point a, and let's approximate where we think we would be at a small time h later. Well, we would start off at f of a. Our instantaneous speed is f prime of a, and we've had h units of time elapse. So the amount we've moved is f prime of a h approximately. And so if our speed was constant, this would be perfect. And so another way of looking at the definition of the derivative is that if you subtract the tangent line approximation to the function, and the limit as that time step goes to 0, this tends to 0. And you can see the two h's would cancel. You get a minus f prime of a that you can pull over to the other side. And that's why it's really the same as these other definitions. And this is the definition that's going to generalize. So rather than just talking about tangent lines in higher dimensions, we have to do planes and hyperplanes. So a line with some triple, say x, y, z is p plus tv. It has one dimension. A plane should have how many dimensions? Two. So we need two free parameters. We'll call them, say, t and s. So one way to denote a plane is I give you some base point p, and then I have two direction vectors v and w, and they can't be in the same direction, and they can't be in opposite directions. But then if I can go any amount in the direction of v plus any amount in the direction of w, that's going to give us a plane. And so you're writing it really explicitly. I can just write it as, if I have two variables, I could call it x1 of my variables ts all the way up to xn of ts. And of course, a hyperplane would just be a higher dimensional plane in the space. So if I had a hyperplane, I could have maybe n-1 possibilities. And we talked about how you can find equations of planes. There's another way you can do it. And this is using what's called the normal method. And so, whoops. Yeah, it just slid it over a little bit somehow. There we go. Okay. And so what we can do is, given some point P, I have a normal direction, something coming out perpendicular to the plane. And then everything in the plane is going to be all vectors starting at P that are perpendicular to N. And what does it mean to be perpendicular? Well, it means your angle is 90 degrees. So we talked before about how v dot w, and we'll review that today, is the length of v, length of w times the cosine of the angle between them. So if they're perpendicular, cosine is pi half, theta is pi halves of 90, so the cosine would then be 0. So what does it mean? Well, then it would mean the dot product would be 0. So the normal vector n dotted with x, y, z minus p, because if you're at the point x, y, z, the gold point, and you subtract the point p, that's going to give you the red vector. And we want that red vector to be perpendicular to the normal vector n. So we want the dot product to be 0. So we get n dotted with xyz minus n dotted with p is 0. So bringing n dot p over to the other side gives us, if we call the normal vector, say ABC, we would get ABC dotted with xyz is n dot p. You just call n dot p, it's something, let's call it d, and you get ax plus by plus cz equals d. So this is another way to get the equation of a plane. And if you think about it, a plane has how many variables? How many free variables? Two. Once you know either x, y, or z, well, that's not enough. But once you know two of them, then you can solve for the third. So, z would be ax plus by minus d divided by c. And of course, if either c, a, or b is 0, then we have to be a little bit more careful. All right, so this is the fast review. So one of the big things we're using is we're using what's called the law, the dot product. So let's quickly review the dot product and see why the formula is true. So if I give you two vectors, say v and w, and let's call this theta vw the angle between them, then v dot w is the length of v times the length of w times the cosine of the angle between them. Whenever you see anything in math, you should always ask, is this reasonable? If I were to double the length of v, what happens to the left-hand side?
Doubles.
Doubles. What happens to the right-hand side?
Doubles.
Both double. So it's reasonable. And again, v dot w is just v1 w1 plus dot 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 plus vn wn. So this is a good way to check and see if the formula is right. What if I flip the order of v and w? Should that change the?
No.
No. Flip v and w, cosine vw might be negative the angle of wv, but same cosine. Because cosine is what kind of function? Yeah, cosine is an even function. So let's prove this. So if I look at this vector would be v minus w, right?
Yeah.
And do we know any formula that relates the lengths of three sides of a triangle?
The law of cosines.
Law of
Yes,
cosine.
we do. Oh no, I was gonna say something. I was gonna say the one with S.
Law of sines.
No, the one where it's like the one with the half perimeter.
Oh, Heron's formula?
Yes.
Yes, that would be good for area.
Oh, areas different. Wait, never mind.
No, but it's good that you know that. And it's either Hero or Heron's formula. They're both
Which one's
acceptable.
that? I might have seen it. I might not.
So the area is equal to S times S minus A, S minus B, S minus C square root, where S is the semi-perimeter.
Is that big S or like both?
That's big S.
Okay.
I believe this is the formula.
Yeah, that's right.
So this
That,
is
that looks vaguely familiar.
Heron's formula.
Nah, you showed that to us last year.
Yep.
That's right.
It's-
That's why it
It's
looks familiar.
extremely useful.
Yeah, that does look familiar. But
Yeah, because you can find the area of a triangle without the angles.
Exactly.
oh yeah.
But
that's
if you
how
think
do it.
about it, if you know the three sides,
You can use the law of cosines to find.
You can still find the angles, but I don't know. I don't like angles, so it's cooler.
it,
You can
it's
use the law of cosines to find the angles and therefore
exactly,
find the
exactly. You can use
triangle,
exactly.
But like, this is a nice
Right.
shortcut.
So one way of looking at the law of cosines is that if you know the sides, you've got to know the angles.
Yeah.
Okay, so how does this help us in what we want to do? Well, no, it does. So fortunately, I can quickly just copy something and just paste it onto the next page. So I don't have to, draw the picture again.
Paste it.
Yeah, the pasting is it's not even, there you go. Okay, there you go. Okay, so now let's apply the law of cosines. So let's let C equal V minus W.
Good choice.
Let's let B equal V. Let's let A equal W. and then theta will be theta VW. So we get c squared is a squared plus b squared minus 2ab cosine theta. And recall, the length of a vector squared is v dot v. The length of w squared is w dot w. And the length of v minus w is v minus w dotted with v minus w. So we did this before. This is just v1 squared dot 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 plus vn squared. This is w1 squared plus dot 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 plus wn squared.
Yeah.
So this is basically Pythagoras.
Yeah.
So we're all comfortable that the length of a vector is just the sum of the squares of its entries.
Yeah.
So this would then be v1 minus w1 squared plus dot 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 plus vn minus wn squared. We all good?
Well, yeah, so long as the formula squares it, which it does. So yeah. It's
Yep.
good.
So now we substitute. So c squared is the length of v minus w squared. A squared is the length of w squared. B squared, I guess put them the wrong way, is the length of v squared. I put the L's to just remind myself that it's a vector. And then I subtract off 2ab, so that's the length of v, length of w, times the cosine of the angle. Well, what's v minus w squared? That, well, if I expand this out, it's v1 squared minus 2v1 w1 plus w1 squared, right?
Yeah.
So when I put this in, I get, if I add all this stuff, I'll get v1 squared plus dot 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 plus vn squared plus w1 squared plus dot 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 plus wn squared minus 2 v1 w1 minus dot
Yeah.
dot dot minus
So
2.
the squareds cancel with the
Yep.
squares.
So you're
and
gonna
the
see that the
twos
square's gonna
cancel with the
cancel.
2.
Plus dot 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 plus vn squared plus w1 squared plus dot dot dot
Don't you love
plus
random
wn
stuff?
squared. I really do. Minus 2ab cosine theta. And as has been remarked, this green stuff here will cancel with this green stuff here. We'll make this gold because I like gold. And the minus signs cancel. And we're left with, the twos cancel. We're left with v1 w1 plus dot 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 plus vn wn is equal to, oh, and ab is just 2, also the 2 canceled, is just equal to the length of v, length of w, cosine theta, and this is just v dot w. So what was nice is I didn't know I was going to prove this tonight, but the proof is just so straightforward that once you start writing it down, if you just do the algebra, you're led to it.
Well,
So this gives us a really nice way to tell if two vectors are perpendicular. So note v is perpendicular to w, I know, if v dot w equals 0. Is it 0 the number or 0 the vector?
right.
When you take
Here's
the
the
dot
dot
product,
product
it's a dot product. So what is the outcome of a dot product? Is that a number or a vector?
number.
It's a number.
0
Okay.
just means that it's because the cosine of, what would that be? Cosine of pi halves is 0.
Is 0. So this is 0, the number, not 0, the vector. Now there is something called the vector cross product, which only works in certain dimensional spaces. It does work in 3-dimensional spaces. It's very useful. We will get to that later.
You have to do it in like the right order, right?
You have to do it in the right order. It has a lot of applications for physics.
And that tells you about sine, or about if they're parallel because it's sine,
Yes.
something like that.
So the definition of the derivative, and then we'll stop after this for tonight. So the gradient of f, we write it as triangle f, or sometimes as grad f. And this is,
Does it have to be like that upside down?
yep,
Okay. That's what I thought.
df dx1,
Normally, like you see like
DF.
the normal.
exactly. So we call this the upside down triangle.
Yeah.
And so it's the vector of partial derivatives. So sometimes we might do, gradient of f is maybe df dx, df dy, df dz if we're in 3 dimensions. Or maybe do the gradient of f at the point, AB might be df dx, evaluate at the point AB, df dy, evaluate the point AB. Or more generally, I might do the gradient of f at some point P would be, df dx 1 at the point P dot 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 df dxn at that point P. Okay? So what we're doing is we're taking derivatives in very special directions. So if I have my coordinate axes, so maybe this is the x-axis coming out, this is the y-axis, this is the z-axis. When I do my partial derivatives, I'm only allowing myself to move along the coordinate axes. Okay?
Yeah.
So this is extremely special. So we say,
So in that sense, it's kind of parametric.
you could view it as, we have our curve, and our curve is limited to move in certain directions. And we're moving only in one direction. In fact, we're moving in straight lines. Ideally, you want to allow yourself to move along any kind of path like this. And we're not allowing ourselves to do that right now. So the definition, we say f is differentiable at a point, a1, an, if the following is true: the limit as h goes to 0 of f of a1 plus h1 dot 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 an plus hn minus f of a1 through an minus grad f at the point A dotted with h divided by h goes to 0. Now, what kind of quantity is h? So here, h is h1 dot 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 hn. What kind of quantity is this?
It's a vector.
It's a vector. I can't divide by a vector, so I take the length of h. What about the numerator? Is that a number or a vector? So I've got f evaluated at a point. Is that a number or a vector?
Number.
Number. So this whole thing is a number. I don't actually need the absolute value, so I'll just put it there. So what we're saying is this is the generalization of the straight line concept. It says for a function to be differentiable, if you move by just a little bit, you can approximate where you are by where you started, plus the gradient, which is telling you how fast you're changing, dotted with h, which is telling you the direction in which you're moving.
It's reasonable.
It's extremely reasonable. So, if I give you, just writing things out, the gradient of f at a dotted with h, this would just be df dx1 at the point A times h1 plus dot 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 plus df dxn at a dotted with hn. So not every Calc 3 course actually covers this. A lot of them completely ignore this and they just say, if your function is differentiable, if the partial derivatives exist, then your function is differentiable. You've got to be a little bit careful because this is not always true. So the function we'll look at today, and this is our last function. Let's see if I can get this right. F of xy is, I think it's the cube root of xy. I'm trying to think if I want the cube root or if I want the -1/3 root. Let's try this. So this is if xy is not 0, 0. I'm a little worried that this might not be good because actually I can use the cube root for all values. So if I want to calculate the gradient, the derivative of f with respect to x, this would be the limit as h goes to 0 of f of 0 plus h 0 minus f of 0, 0 over h. Well, what's f of 0 plus h? Comma 0. So if x is h and y is 0, what is that going to be?
Right.
So if I take f and I evaluate the point 0 plus h 0, that means take x to be 0 plus h. So x is h, y is 0, and take the cube root. What will that equal? What's the cube root of h times 0?
0.
0. So I would just get 0. And similarly, I would get, df dy would also equal 0.
Yeah.
But if I consider the path y equals x squared, what is f of x squared equal to? So if x equals x and y equals x squared, what's f of x? Yeah, it's just going to be x. So now, if I were to take the derivative of the function x, what should I get?
1.
1.
Yeah.
So would expect along the path y equals x squared, the derivative should be 1. Does that seem reasonable? Zeke, does that seem
Yeah,
reasonable?
yeah, sure, yeah.
But if we look at this function, let's just try to differentiate this function. So we have f of xy is xy to the 1/3, 0. What should df dx be if we're not at the point 0, 0? If, say, x is greater than 0, y is greater than 0, what would that derivative be? So I want to consider, this is just x to the 1/3, y to the 1/3. So if I'm taking the partial derivative of f with respect to x, y is constant, right?
Yeah. So it'd be 1/3
1/3.
x to the minus 2/3 y 1/3.
So notice, if x is greater than 0 and y is greater than 0, depending on how x and y go to 0, this can blow up. Because this is just going to be 1/3 y over x squared to the 1/3. So if x is decreasing much faster than y, then x squared is going to be much, much smaller than y. So this is going to blow up. So what we have is we have the strange situation where if x is greater than 0 and y is greater than 0, what is df dx if y equals 0? Well, if y equals 0,
Sure.
then my function f of xy is just always 0. So this derivative is 0. So notice df dx is not continuous. There are problems as we hit the axes. Okay. So this is just some technical stuff. It's good for you to have seen this at least once in your life, just so you know why we have to be a little careful in mathematics. Is we can have functions whose partial derivatives exist, but the function is not differentiable. For us, differentiable means that the tangent line approximation is so good that even when you divide by how much you moved, that tends to 0. Have you guys seen The Simpsons?
Yeah. A little.
Have you ever seen The Simpsons, Zeke?
No,
You've never seen an episode
Oh,
of The
you need to see an
Simpsons?
episode.
I haven't, and I don't really want to, but that's not
I've seen
that's
like
not
an
as an
episode here
offense.
and there.
It's just like it's like The Simpsons, Family Guy,
Yep.
like South Park. They're all just like variations with like different maturity of audiences of the same
You should
Yeah.
see at least like an episode of each of those.
Yeah. But
Like,
they,
you don't have to like watch
Right.
everything. Just see a little bit.
but there's one episode where it turns out the principal of the elementary school, Principal Skinner, is actually not Principal Skinner. So Principal Skinner was, I think, fighting in Vietnam, and somebody came back, and his life wasn't going well, and he pretended to be Principal Skinner. And it comes out, and at the end of the episode, everybody says, "Well, we know you're not the real Principal Skinner, and we know this person over here is the real Principal Skinner, but we like you more than him. So we're going to ignore him, and we're going to treat you as the principal, and none of us will ever talk about this ever again." And everyone agrees. And for the rest of the series, they've never talked about the fact that Principal Skinner is not Principal Skinner. It's kind of like that, what we just did tonight, is I wanted you to see you've got to be careful in math about how you define things. That things that seem intuitive, oh yeah, function's differentiable if the partial derivatives exist. That's not always the case. This is why we have to be careful as mathematicians. Now that we've done that, now let's just play fast and loose with the math, and let's just take partial derivatives and see applications. All right, good night.
Thank you. Good night.